And thank you all for coming. I would like to recognize some of the people that I've worked with over the last several years related to this lecture and to the projects just mentioned. We've come a long way since the first lecture 5 years ago by Dr. Janet Cavanti to today's lecture, who is a Nobel laureate. Where'd I go from here? I don't know. Let's see. I would like to recognize the Brewer Science people. Thank you for coming, and MOSI people as co-sponsor of this event. And now for my co-workers, the late Dr. Tom O'Keefe was the co-advisor for all the students with me. He's a metallurgist, and I am a chemist, coatings chemist, paint chemistry, if you will. He was the co-advisor for all the students. He had a postdoc by the name of Dr. Paul Yu, and I had two students, one of which was Dr. Eric Morris and Dr. Scott Hayes. They did if you understand that, you understand who did the work. It was the students. The research involved was the goal to find a replacement for chromate conversion or chromate coatings. Chromate was the corrosion inhibitor in paints used on all aluminum aircraft. If you didn't have paint there, the aircraft would get corrosion and not be flyable after a year or so. Chromates are cancer-causing. If you saw the film Erin Brockovich, that's real life. We were fortunate in getting grants from the Air Force. First grant in 1998 was $1.5 million, and subsequent years after that we had about $5 million in research grants. More importantly, we found a replacement for the chrome systems based on our work with cerium and praseodymium oxides. Obtained several patents, and that is a story in its own right. Licensed the technology to DEFT on the West Coast. Eric, the student who did the primary part of this work, went to work for DEFT, and he's still working with them, although he changed companies because the technology was bought by PPG. It has produced some $3 million of royalties to the university. Money from those royalties helped pay for this activity. For example, the chemistry department got $50,000 for its E&E package last year alone from the royalties. So it's worthwhile in that sense. And I've been benefiting from it too, and I'm thankful for that. Now on to Dr. Schweitzer, who's going to introduce the speaker.
Okay, thank you, Jim, and thank you for endowing this seminar series. My name is Jay Schweitzer. I'm in the chemistry department and the materials research center, and it's my distinct honor to introduce our speaker today. Our speaker is M. Stanley Whittingham. Stanley was born in England, and he got his education in England, his bachelor's, master's, and doctor of philosophy from Oxford. I should mention, first of all, he's a distinguished professor of chemistry at Binghamton University, and he's the director of the DOE-sponsored Northeast Center for Chemical Energy Storage. So anyway, going back to his education, he got his education in England at Oxford, and then he came to the US and did a postdoc with Bob Huggins at Stanford, where he worked on intercalation chemistry, which I think set the foundation for his later work on batteries. And then actually after that, worked for 20 years in industry, 16 years at Exxon and 4 years at Schlumberger. And at Exxon, he actually developed the first lithium-ion battery and patented it. And then like I say, moved on to Schlumberger. And then it's not until actually 1988 that he joined Binghamton University after 20 years in industry. So normally you try to think of some honors, to announce that this person has, and that I could go through a whole list of things, but I'll just do three. Okay, so in 2018, he was elected to the National Academy of Engineering. In the same year, he did the Nobel Lecture in Materials at the Materials Research Society. And then in 2019, he won the Nobel Prize in Chemistry with John Goodenough and Akira Yoshino for development of the lithium-ion battery, which, as you know, is a pretty big deal, right? So today, he's going to talk about the origins of the lithium battery and future chemistry and material science. Thank you. Dr. Whittingham.
Okay, thank you very much for that, those nice words. And I'd like to thank Professor Stoffer for endowing this lecture series and making it available to the students. What I want to talk about is really the origins of the lithium battery and all the challenges still ahead of us, and how lithium batteries and all of us can help solve some of the climate issues we have today. But let me first of all thank the US Department of Energy. They've supported my work for now 30 years. And okay, let me just get this. The right one here. Okay, so I'll go back to 1972 and bring it up till to date and show you how we got to where we have, and look at the potential impact on the cleaner environment, both vehicles and renewable energy, and how it can really help us, give us more resilience to natural disasters like we've had in Texas, like we had with the hurricane in New York City. I'll discuss what they are, what the limitations, and then some opportunities for today's students. So let me go back right to the beginning and really thank what was then Esso, then went to Exxon, now ExxonMobil, who had the foresight and wisdom to invest a lot in alternative energy. They worked on fuel cells. We got them involved in batteries. And they were, that in the 70s, the largest manufacturer of solar photovoltaic cells in the United States. So they, at that time, wanted to become an energy company, go beyond petroleum and chemicals. So what we worked on initially were these crystals here. This is titanium disulfide. This is what we actually used in the battery. And the two of the examples of the batteries we built in those days are shown here. At the top, this is a paperweight we gave away to potential customers. You can see it has a lithium battery here, coin cell, a watch, and a little solar cell. This particular one is on my desk right now and still working, and it's probably about 45 years old. So very well-made lithium battery can last essentially forever. The larger one here is about 6 inches by 4 inches by about 1 inch thick. And this we used at the electric vehicle show in Chicago in 1977. So electric vehicles were very hot in the 70s. So those of you old enough to remember, we had a gasoline shortage in the 70s due to wrangling between Saudi Arabia and the United States. So these turned a motorcycle headlamp on and off all week long, and we had no issues at all with them. So they're quite successful there. Remember this little battery here? If you want to see this now, you'll have to go to Stockholm. Bob Hamlin, who was in charge of manufacturing and engineering, and I searched our basements and found one of these coin cells and a button cell. And in fact, we had these tested by Glenn Amatucci at Rutgers University, and they still retained over 60% of their capacity after 40 years. So very good. This is the technical brochure we had, which we gave away to potential customers, which described essentially everything in these two cells. So let's look at where we've gone from That was about 1976, 1977 till today. And I show you a series of vehicles here. A two-seater. This is one in Bermuda. My wife and I had our 50th anniversary there 2 years ago. And probably many of you know you cannot drive as a tourist cars on the island, but they changed the rules if you had electric vehicles. And this one had been on the island for about 2 weeks. So we tried it out and it was fine. We weren't going to ride mopeds. At the opposite end of the spectrum are these two large trucks. This is a standard 16-wheeler, and these are lithium-ion batteries in it. And this is a garbage truck. And the garbage truck is really ideal for electric vehicles because stop, start, up and down all day long. And these were at the Packard facility about an hour north of Seattle. And I got the chance of driving both these around their test track. To put in perspective what other countries are doing, the UK ambassador brought 2 electric vehicles to Stockholm for the Nobel ceremonies. This is a Jaguar, and the right-hand side, you can probably recognize this is a London taxi. And she used this to go to and from the palace. Britain has outlawed the sale of internal combustion engine cars after 2030, probably the earliest of any country in the world. Energy storage also, as I'll show you in a moment, enables renewable energy, solar and wind. And I show you a facility here in West Virginia, which is probably about 5 years old now, a wind farm. And here's the batteries that smooth the wind energy and also allow it to be shifted by many hours to when it wants to be used. A final recent use of lithium-ion batteries in a very rigorous environment is on the International Space Station. And 2 of the physics Nobel laureates and I had a chance of talking to them live whilst we're in Stockholm. The lady is from the state of Maine and her mother was Swedish. The fellow is from Italy, and they had just finished installing lithium-ion batteries on the outside of the space station to store the solar energy, replacing nickel metal hydride. They are very pleased because they weigh half as much, take up half the space, and should last twice as long. So lithium-ion is basically going everywhere. So let's just look at renewable energy at the moment. People ask, is it viable? What's happening? And the answer is it's very much viable. And I choose here an example from the state of Texas at the top. Not exactly a clean energy friendly state, certainly in political terms. And on the right-hand side is the new generation capacity as of last August that they plan to put on the grid. And 94% of that is renewable. You see solar, wind, and storage. A little bit of gas, but essentially nothing else. The big advantage of renewable, there's essentially no cost during operation, unlike a coal, oil, or gas power plant. Now, 3 or 4 weeks ago, it was announced in the press that Tesla was installing a 100 megawatt facility in Texas. Tesla itself is staying very quiet on it, but these are the pictures the press got. So even their storage is going in. Put that in perspective, in Moss Landing, California, last December, a facility opened up, which is 1.2 gigawatt hours. This is about 4 times the size of the next largest facility in the world, which is also, I think, Tesla, either in San Diego or in Australia. This particular facility replaced a gas-powered plant, which is mostly, I think, a peaker plant, which filled this building. This building is now filled with lithium-ion batteries, more on the outside. And the reason this one is, I think, economically viable is because all the grid infrastructure is already there. So it's almost plug and play. They have plans to expand this to 1.6 gigawatt hours this year, and it's approved to go up to 6 gigawatt hours in the future. So huge size, by far the largest anywhere in the world. Let's just look at the big energy picture. What we do is we produce energy. If it's oil, gas, or coal, it's a one-time use, certainly in our lifetime. If it's renewable, we can think of at least of solar, wind, and hydro. It's free but intermittent. The next challenge is really distributing that energy. The source and use are rarely in the same place. I think with solar, this may be possible to change. So we have to understand how to transport it and how to store it. And demand and use are not uniform. In other words, when the energy is generated is not necessarily the same time as we want to use it. We have to handle that. And the other challenge is all of us, we want instant gratification. So we have to be essentially more energy efficient. Most of you probably don't know that North America uses 4 times as much energy per capita as Europe does. We should be able to do that better. But at the same time, we have to find a way so utilities can still make money as energy use drops. In New York State, utilities make money on their capital investment, not on how many kilowatt hours they sell. So they've got an incentive to improve efficiency. So let's look at what the demand is. And this is a typical usage profile. It's a very old one, but I can tell it hasn't changed. So if you start at midnight, go through the daytime back to midnight, very low demand at nighttime. It comes up as we get up and start working. And then around about 4 o'clock to 6 o'clock, we have this peak demand. People are still working. People are now turning on everything at home as well. The challenge is here we have to build power plants to address this peak today. So the goal is, in fact, to store energy, store the energy in the middle of the night, as we've shown here. So the red period, knock off this peak so we can get rid of these peaker power plants, which maybe only use 5 or 10% of the time, and often are the dirtiest power plants out there. So we can get rid of those, will clean the environment up a lot. Using solar and wind helps, but they don't exactly shift the time load for us. So wind is highest in the middle of the night, particularly in Texas. So we have to store that energy and move it across to the daytime. Solar peak is in the middle of the day. And right now, places like California are already generating more solar energy in the middle of the day than they need. So solar prices for their energy is dropping. So they need storage. And if we do that, then we should be okay. And the other area that we can obviously store a lot of energy and we have to use is pumped hydro. If we look at all the storage means in the United States and around the world, by far the largest is pumped hydro. We're talking about gigawatt size facilities. I show you a picture here of one that's about 1 hour from me in Binghamton. There are several others in New York State, in Pennsylvania, in the Tennessee Valley. So these are often used for what we call seasonal variations. So we use a lot more power in the middle of the winter, in the middle of the summer, and not so much this time of the year and in September, October. So these reservoirs tend to get filled up in the spring and fall, and you'll find them getting pretty empty in the middle of the winter and summer. These now are extremely efficient, more than 73% of the energy you put in, you can get back out, and this with modern turbines. And I expect this may get even better. The challenge is in the US, there's limited new sites. Batteries are by far the most flexible and common. They can be portable and stationary. We can go from milliwatts in little card devices to gigawatts, and we can switch them off in a fraction of a second, unlike the pumped hydro where we need 2 minutes. thereabouts. So even if we're going to turn on a pumped hydro station, we need batteries or something else to provide that energy for the first 2 minutes. The third area where there's been some action is flywheels. So we convert kinetic to electrical energy. This is most useful for power smoothing, not for long-term storage. They're hazardous. They're like a very large hand grenade, so they tend to be built in concrete bunkers. There's one operating near Albany, New York. It cost so much to build, the company went bankrupt, but another company bought the facility and they're now making money and it's working. But it's not long-term storage. So let's now start looking at what a battery is and how they can fit into this scenario, and that'll give us some chance at talking some scientific opportunities. All of today's lithium-ion batteries work on what we call intercalation chemistry reactions. If you've got an old dictionary and look up the word intercalation, you'll see it associated with the addition of a day or a month into the calendar, most commonly putting February 29th in every 4th year, then taking it back out and you can't tell any difference. So in chemistry, it's used in exactly the same manner. It's a totally reversible chemical reaction where you insert some guest species into a host lattice and take them back out. And if you look at it afterwards, it will look identically the same. The guests can be ions or molecules. The hosts can be inorganics, DNA, whole range of things. And this book that Alan Jacobs and I edited in 1982 is still available, and it costs much more today than it did when we published it. But the key thing here is, if we look at an intercalation reaction for a battery, again, I'll look at TiS2. Here we have van der Waals bonding between each TiS2 sandwich, and the lattice is 5.7 angstroms. Put lithium in, expands to 6.2. So we just get a 10% expansion. Remember that 10%, because I'll come back to it towards the end of the talk. And if we take it back out, it'll go exactly back to this 5.7. So let's look at the key components of a battery, and I'll stay with TiS2 for the moment. So we have the anode, which is, in this case, will be pure lithium. Most of the batteries today, in fact, all of them, use a graphitic carbon in here as shown. And the other electrode is a cathode. And this will be TiS2. I'll show you a number of examples of what's used today. And then we have the green circles are the lithium ions that fully charged, all in the anode. When you discharge it, they go through an organic electrolyte. It's important to remember this is a lithium salt like LiPF6 dissolved in the organic carbonate particularly, and diffuse over to the cathode, and the electrons go through the external circuit. So a key feature here, electrons have to move. So these materials, both the anode and cathode, have to be electronic conductors as well as ionic conductors for these intercalation reactions. So let me just show you a bit more about TiS2, why it's special, why there's still interest today in it. For those solid state chemists of you, it's described by the physicists as a semi-metal, which for all electrochemical purposes means it's a metallic conductor. This means the electrostatic charge on the lithium when it diffuses through the lattice. That's here. Sorry, the lithium ions have changed color, but they diffuse through here. They're shielded from the charges in these layers by the electrons, so they can move very fast. In addition, this particular material is a single phase, all the way from 0 lithium to 1 lithium. So this is your discharge curve, slopes all the way. It's an indication of a single phase. And what is happening, you're putting lithium into the van der Waals gap, and we're putting electrons into the conduction band. And as we fill that conduction band in, we get less and less energy out, so the voltage drops. When we recharge it, you see it follows exactly the same shape, showing it's completely reversible. The difference here is just the resistance loss in the electrolytes. Two things I want to point out. We can run this at 10 milliamps a square centimeter, which is probably about an order of magnitude than today's lithium-ion batteries work because it's a metallic conductor and because we don't need to add any carbon diluent to it, also because it's a metallic conductor. Today's batteries all have carbon black or acetylene black or graphene or something like that mixed into it. So it's an ideal cathode from that point of view. And here's some of the Exxon team I worked with. Art Thompson was a physicist. John Pinella was my technician. Russ is a solid-state chemist, as is Alan Jacobson. Marty Dines was an organic chemist. He'd worked on the electrolytes. Bernie Silbernagel was a physicist, and he did NMR and other characterization studies. Fred Gamble was an intercalation chemist. And Al Schriesheim was our director. Al was, after he left Exxon, was director of Argonne National Lab for a lengthy period. And I gather, very successful director. So let's look at where else TiS2 has been looked at. Brian Steele and his students looked at the sodium analog. And now you can see, unlike the nice smooth curve for lithium, the voltage is much more complex here. This is showing we get multiple phases formed, a second stage, trigonal prismatic coordination of sodium, and octahedral coordination. Much bigger voltage change, so much less interest. More recently, Linda Nazar, Waterloo in Canada, was looking at magnesium batteries. And because of this soft lattice of TiS2, magnesium can diffuse through this material. And you can see similar behaviors, titanium disulfide, more than 40 cycles, 100% Coulombic efficiency. But it's not really viable as a battery, but it tells us a lot about diffusion mechanisms. You notice the voltage of this cell is about 1 volt less than lithium. So you also had to run it at 60 degrees centigrade and at a much lower current. But it shows the feasibility of intercalating a divalent cation into these lattices. TiS2 and its analogs are also of great interest these days for lithium sulfur batteries because they can act as a conducting electrochemically active substrate. Let me very quickly explain why we don't have lithium batteries today. When you electrodeposit any metal, you tend to form dendrites. And I show you one here, which is an optical study Russ Chianelli did at Exxon back in the 70s. And as soon as these form, they all penetrate almost every separator between, this is the anode and the cathode is off the page over here. So we have to solve this problem. And this problem was manifested in some all solid state batteries made by Avastor in Canada. And they were used by AT&T in some housing developments. And you can see these were just after a few weeks of operation. They got dendrites, short-circuited, and burnt up. These same batteries have now been improved and they're used by Blue Solutions in cars and buses in Europe, and I'll show you a picture a little bit later. So lithium went out and graphite was used as an intercalation compound for the anode. So let's just look at that progress. Now go through this fairly quickly, you're probably familiar. So Exxon started out with a lithium anode. We recognized dendrite problems, switched to aluminum. So we could form a lithium aluminum alloy. This works well for maybe 50 to 100 cycles, but lithium aluminum is very brittle and tends to powder. Akira Yoshino in Japan was working on polyacetylene in batteries and then worked out that graphitic carbons could store lithium very well, and this is the anode. Today, this has to go because you need 72 grams of carbon to store 7 grams of lithium, and the anode takes up half the volume of the cell. So there's a lot of work at looking at tin or silicon, both of which react with more than 4 lithiums, and most people would like to get back to the holy grail of pure lithium. The other thing I'd like to point out here, it took from 1972 to 1991 for lithium-ion to be commercially successful. There are a number of ventures in between, but it's really Sony, a vertically integrated company that wanted a battery for their various devices that put in about 5 to 10 years of engineering to make it safe and viable. On the cathode side, we worked on TIS2. John Goodenough, who was then at Exxon, not at Exxon, at Oxford, sorry, was studying the magnetic behavior of cobalt oxide. And he recognized it had a similar structure, so tested it out in an electrochemical cell. And we all know what happened then. Since that time, there's been a big push to remove as much of the cobalt as possible. And I'll get into that in a moment as well. And it's replaced by nickel and manganese, so these are known as NMC, or in the case of Tesla, by nickel and aluminum. About 20 years ago, John Goodenough also came up with these olivine compounds, lithium iron phosphate, and showed that they could be used. The challenge here, and you'll see it in the slide, the energy density of these is much, much lower than that of the layered oxides, because you've got the heavy phosphate group and lower voltages. So lately we've been looking at using phosphates because they're safer. And again, I'll touch on that in a moment. But to use them and make them viable, we're looking at putting 2 lithium ions, so we only need half the transition metal per electron. So let's look at what the incentive is. A lot of people ask, you've got the Nobel Prize, okay, research is finished on batteries. It couldn't be further from the truth. So let's look at these numbers within this oval. These numbers are the percentage of the theoretical capacity that today's cells have. So this is lithium iron phosphate, 11 to 15%. The best one here is a cell based on nickel, manganese, and cobalt, 80% nickel, and using a mixed silicon carbon anode, and we're getting 25%. On the weight basis, they're all again about 25%. So there's plenty of opportunity, and I'm part of a large consortium called the Battery 500 Consortium, and the goal there is to get this number up to 500 watt-hours per kilogram. And I'll show you next how we're going to achieve that and some of the other challenges that generates. But to get there, we've got to eliminate a lot of this carbon. We need to use materials that have higher lithium content, and the layered oxides, you're only using about 60 to 70% of it. I've already talked about 2 lithiums. We need materials that are better ionic and electronic conductors. Neither of these are good electronic conductors. If we could have them better electronic conductors, we could make thicker electrodes, which would reduce the amount of current collector and separator. So plenty of good science right there. So let's look at what the challenges are. And this is, I think, a fairly famous figure now in the battery literature. It shows basically the capacity of a cell versus its thermal stability. So if we look at these layered oxides, and let's say these can be nickel, manganese, cobalt, aluminum. Typically, we call them NMCAs. The name given to these depends on how much of nickel and the rest they have in it. And then I show an example here. So if we're talking about 622, that just means 60% nickel, 20% manganese, and 20% cobalt. The challenge we have here, if we look at the bottom axis, the highest capacity is the highest nickel. So this is 85% nickel. This one will evolve oxygen on charging above 220 degrees centigrade. The safest material only has 1/3 of a nickel in it, but it only has 160 milliamp hours per gram. So there's a huge trade-off. And our goal is really to get this attribute, and move over to here. So I should emphasize clearly you don't want your battery ever getting this hot, but the thermal stability is that direct measure of the reactivity of the material with the electrolyte, which gives a measure of the capacity retention. So our target is to get to high nickels above 80% And there are two reasons for doing that. One is obviously energy, the other one is cost. Cobalt is by far the highest cost element in the batteries. So companies are eliminating cobalt as fast as they can. There's also major environment issues with cobalt. A lot of the cobalt is mined using child labor in the Congo, and most companies don't want to have anything to do with that. So they want to eliminate the cobalt. So if you're looking at vehicles today, they've gone from 1/3 nickel to 60% nickel, and some are moving into the 80% nickel. But we have to address these challenges of reactivity and safety. So let's look at where we stand in our battery 500 consortium. As I say, we're trying to get to 500 watt-hours per kilogram. This is a large consortium of about 10 different institutions led out of Pacific Northwest National Lab. We chose one material as our standard material to begin with. This had 60% nickel in it, and our goal was to achieve 350 watt-hours per kilogram in the first 3 to 4 years. And this material is typically formed in what we call a meatball morphology. So the primary particles are about 100 to 200 nanometers across, giving you surface area for reactivity. But to give packing density, the secondary particles are from 5 to 20 microns across. So here's the data we've got. In our first year, 2017, we achieved 300 watt-hours per kilogram, and we got about 50 cycles. The next year, we exceeded 200 cycles, again at 300. 2019, we pushed the energy up and got to 350, also about 200 odd cycles. And last fall, we achieved 350 watt-hours per kilogram, but somewhere over 400 cycles. So we can increase the energy density above today's 250. I should emphasize we're using a pure lithium metal anode, and we're using a new electrolyte based on ether systems. This work was done by an ex-student of mine, Jay Xiao, who is at Pacific Northwest National Lab, and the test at Idaho National Lab. So to make sure everything's independent, we make cells in one place, test them in another one. And this is a typical cell, 2 ampere hour pouch cell. And to get these energy densities, we weigh this package, so it's for real. And we measure its volume. So its volumetric energy density is about 700 watt-hours per liter. But to get even higher, we've got to use all the material. We're not using it all in these layered oxides today. So first, to get more material, we go up to 80% nickel, as I've shown you here. But in all these layered oxides, these NMCs, if you charge them up, as we do here, typically to about 4.4 volts, above that, the electrolyte starts decomposing. Then discharge them, you find out you lose between 10 and 20% of the capacity on the very first cycle. And we need that capacity to get above 400 watt-hours per kilogram. This capacity is also in this 3.5 volt region, which is the most stable region of the electrolyte. So we set out to understand what caused that. So we measured the diffusion coefficient of the lithium ions going in the solid circles, lithium ions coming out the open circles. And you can see, taking the lithium ions out, very steady, constant diffusion coefficient above 10 to minus 9. But as we put them in, above about 70%, this diffusion coefficient falls off by more than 3 orders of magnitude. I think you can understand it, probably not today, but in a normal time, when your lecture hall is completely full, by this time 70% of the seats are filled, the empty seats are probably in the middle somewhere. So everybody has to move to let the next ones in. And in the case of these lithium ions, according to Anton van der Ven, it's a divergency mechanism, so we need 2 empty seats for a lithium ion to move, hence why it falls off so fast. To confirm this was diffusion, we did some studies over temperature range. First of all, at room temperature, we charge these to different voltages. So you can see if we charge to 4.2 volts or 4.8 volts, we get much more lithium out at 4.8 volts. But at 4.8 volts, you can see these charge and discharge curves are separating, which means we're reacting with the electrolyte and forming resistive films. There's a little bit of that at 4.4 volts. And to test the diffusion mechanism, as you discharge, we then hold it at 2.8 volts, see how much more lithium we can get back in. So you can get quite a bit more back in by holding it again, telling it as it's diffusion controlled. But if we increase the temperature to 45 degrees centigrade, we in fact get a bit more capacity, but you now see this first cycle loss is substantially reduced at 4.4 volts. It's reduced a bit more at 4.6 volts, 4.8 volts is worse because now we're getting even more side reactions. So really with the present electrolytes, we're restricted to 4.4 or 4.5 volts. We can't even go to 4.6 or 4.8 volts. So if just going from roughly 21 degrees to 45 can solve this problem, then we ought to be able to modify the material to solve it as well. And there was another clue that we should be able to solve it. Pure lithium cobalt oxide does not have a first cycle loss. So here's our 80% material, same data I showed you before, except now we just charged it to 120 milliamp hours per gram, and then held it for 100 hours, that curve, and we got all the lithium back in. At room temperature, you can see we almost get it all back in without having to hold it. Exactly the same experiment on lithium cobalt oxide, essentially no loss at all. So we just had to find a way of modifying the NMCs to make them behave like cobalt oxide. And we believe we can do this by substituting in the lattice or coating on the surface of the lattice. And what I show you here is a coating using a lithium niobium oxide solution. So we soak these meatballs in the solution, either 1%, 2%, or 3% solution, and thaw it at 500 degrees centigrade. Then we make this brown coating I show you on the outside. At 500, it diffuses a little bit into the material. And what we found with a combined X-ray neutron study, that's not just a simple coating. The niobium, when it goes inside the lattice, displaces some of the manganese, which now goes on the outside. So we have a mixed phase on the outside. And you can see even at the 1% level, we've almost eliminated 50% of this first cycle loss. So we think we can eliminate close to all of it. We're still researching that and pushing it. Let's move on and look at some other materials. I discussed TiS2. Following TiS2 was molybdenum disulfide. This was work coming out of British Columbia, out of Vancouver. This is molybdenite, a naturally occurring ore, and they commercialized this material in a company called Molly Energy and sold cells for many years, long before cobalt oxide came out. But they had dendrite problems and eventually stopped. I've talked about cobalt oxide and MCA. This is the other compound John Goodenough came up with. A tunnel structure, lithium iron phosphate, can take the lithium ions in and out. Both the lithium compound and the FePO4 are both naturally occurring minerals. So it's no surprise that lithium can go in and out. It shows essentially no first cycle loss. So again, a clue that we should be able to solve that first cycle problem. So we decided to look at vanadium, and we chose vanadium because we know vanadium can go from 5+ to 4+ to 3+. We can go over 2 redox couples. And obviously I wouldn't be talking about it unless we had succeeded. And 2 of our students, and this is an EFRC again, about a 10 institution consortium, This is one of my students, and this is one of Claire Gray's students from Cambridge, received an award from the Undersecretary of Energy in 2019 for one of the science highlights of the previous year. So obviously the students were happy. It gave a lot more visibility to battery science in the community. So let's look at this particular material. It is a tunnel structure like lithium iron phosphate, but now the tunnels are in all three directions, so there's no chance of blockages. And I said we can go from vanadium 5 to vanadium 3. It's very easy to make once you know how, and I say that for the students' benefit in the audience. It took us 2 to 3 years to make, I would say, battery effective material. So we dissolve all the reactants in the solution, in this case 95% ethanol, with about 5% of water to stop over-reduction of the vanadium. Heat it at 180 degrees for 3 days. This is in a sealed reactor, so there's about 3 to 5 atmospheres pressure inside, just generated by the solution. And then we form this nice crystal structure. Where we want lithiums, this now has protons inside it. If we treat this at 550 degrees centigrade, we can get all the protons out of this structure. And so we did a fair amount of basic science on this structure. And if you're going to do basic science, you don't really want to do get the materials from a discharged battery, because they'll have carbon in them, bits of electrolyte in them, binder in them, and a lot of other things. So at Exxon, we developed a number of what we'll call chemical clean reagents. One of those that we used was butyl lithium, and this is dissolved in hexane. So if we react vanadium phosphate with butyl lithium, we get 2 lithiums in it. The products of reaction are octane or butane and butane. So very easily gotten rid of. So you can get very clear, beautiful X-ray patterns. You can measure physics properties as well. Key point I mentioned at the beginning, remember the TiS2 expanded by 10%, just as graphite does. This material only expanded by 8.5% as we put the 2 lithiums in, which gave us a lot of encouragement that it should be stable and not give us any problems. So what does this material look like? Here are these little cuboids we formed. These are 100 to 200 nanometers on the side. Okay, very, very uniform. There's phosphate, so it's a very good electronic insulator. So we have to make a conductor. And what we found was very effective here was to mix it with graphene, much more effective than carbon black. And then this is the electrochemical behavior we got out of this material. So you can see we got the vanadium 5 to vanadium 4 plateau here. This is a single phase reaction, which does give us some problems because the rate is low. Then we go from V4 to V3, and you see a number of bumps in here. These bumps are the tendency of the lithium ions to try to order in the lattice, and we can derive the X-ray structures at each one of these different points. But much more important here, when we start discharging this or charging it in the batteries, because we've got these semi-ordering points, this behaves as a single phase reaction. So we can get extremely fast reaction in this lower voltage regime. And I should say there are 50 cycles here. And the first thing to note, the black is the first cycle, the purple is the 50th, and if anything, it's behaving better on the 50th cycle than on the first cycle. So this shows proof of concept that we can stuff 2 lithium ions into a lattice without damaging that lattice. And we've done it more than 50 times now. So we're quite comfortable that we can have these materials work well in batteries. We do have still some issues with this material, mostly because it's a commonly known oxidation catalyst used in the chemical industry. It has a tendency to oxidize the organic solvent using the electrolyte. So we get overcharged. We have to find a good solvent, which it doesn't oxidize. But we're working on that right now. So what are my conclusions and what's going to happen in the next 5 to 10 years? I know there's a lot of research going on to try to displace lithium intercalation systems. Everybody believes they're going to dominate for the next 5 to 10 years. That's partly because there are billions of them made every year. The cost is dropping by about 10% every year. So it'll be very difficult for any other system to get into the market unless they can find a high price market to get in first and then drop the price later. The layered oxides are going to be dominant, but it looks very much like the phosphates. Their market is increasing because there's this need to get the cobalt out. There's this need also to, in the end, to get nickel out. And I'll come to that in a second. But the markets are increasing in China dramatically. They dropped off in the last 5 years on the phosphates because the Chinese government was subsidizing the oxides. They're now subsidizing everything equally, so they're coming back. The advantage of the phosphates, they're much more stable and therefore safer. They don't tend to evolve oxygen. We need safe and stable electrolytes. The present electrolytes is the same one that was commercialized in 1991. It is the source of most of the fires that you see. So the question really we're all addressing these days is, can solid state give the required power densities? And obviously some people think so, and Blue Solutions is making those same cells I showed you a while ago that caught fire with AT&T. They're using much thicker electrolytes, and this Mercedes bus will be using all solid state batteries by the end of the year, and they're switching as an option to solid state because the bus can then run all day long without being charged. So this will use a pure lithium anode, a polyethylene oxide, electrolyte, and lithium iron phosphate as the cathode. Key areas for students and others to work on is we need new manufacturing technology. Right? For that, I mean all the way from the mine to the final product. Today, it takes 60 to 80 kilowatt hours of energy to make 1 kilowatt hour battery, and the materials typically circulate around the globe 3 times before they get into the final product. So we need to look for better materials, better cells, and better ways of making them. And Europe in particular is putting a lot of effort into this. They're spending several $billions to generate a regional supply chain, regional manufacturing. So they intend to do all the energy intensive manufacturing in Scandinavia using clean hydropower. They'll make the final materials and batteries, for example, in Germany, right next to the car plants. And US and Canada and Mexico need to get together to do the same thing here. We also need clean recycling technologies. We can't keep throwing away all our cell phones into the dump. Some dumps probably are richer in cobalt than the cobalt mines. And this will then give us a sustainable society. And I suspect within about 10 years, in some major city centers, you'll only see all electric vehicles. For example, FedEx and Postal Service will go all electric, keep things cleaner and quieter. And a lot of those folks living in high-rise buildings will have shareable cars where you'll hit your iPhone, the car will come to the front door, pick you up, drop you off, then go off to the next passenger. I've just got a couple more slides. One message for the students in the audience. And these came from the banquet speech I gave on behalf of John Goodenough and Akira Ishino in Sweden. The point is all the exciting science, I think, is at the boundaries of our present disciplines. If you're looking at chemistry, exciting areas in chemistry are the boundary between chemistry and materials or chemistry and biology. And I point this out because I'm a chemist by training, John Goodenough is a physicist by training, and Akira Yoshino is an engineer by training. Science these days is also international. It again knows no boundaries. If you want to travel the world, become a scientist, and you can probably do it. And I point out, I'm as you can probably hear, British by origin, but I made my inventions in the United States. John Goodenough was in fact born in Germany of American parents, but made his inventions at Oxford in England. And Akira Yoshino made his inventions in industry in Japan. Just a few other little points. Energy storage is going to enable renewable energy. It's going to help us mitigate what I call global messing up. So we know it's not just warming, it's getting extremes on both ends. As my garden and my neighbor's garden attest, a lot of our plants got crushed by 4 feet of snow last December. And it's going to let us have a more efficient and resilient grid. Two other things for students to keep in mind when they grumble about taking gen ed courses. Because we work across the globe, we work with different disciplines, it's important to understand the culture of others. Now, Americans and Europeans don't think quite the same, and certainly both of us don't think or act the same way as Asians. So we have to understand that. And facts and science do matter, so we need to educate the public about scientific matters in a manner that they can understand. And finally, if there's some students who would like to learn a bit more, there are 2 articles here. This IEEE proceedings volume, published 9 years ago now. It's fairly up to date. Everything in it is fairly correct, but it'll give you an impression. But the key thing about this proceedings volume, any area of engineering you're interested in, there's a chapter on it. And this proceedings volume is totally open on the internet. It was their centennial volume. So if you want to know about solar cells, chips, or anything else, you'll find a chapter on it. This book called Bottle Lightning really gives a history of the lithium battery up to 2012. It's probably the best book because it's not hyped. Now, the author isn't trying to make a reputation for himself. And it's about, I think, $8 or $9 on Amazon and easy reading. And I will stop there and try to answer any questions you might have.
So I guess, well, before anybody else comes down, there's a microphone right here if you'd like to ask a question. But I guess I was wondering, when you were doing this work at Exxon, were you tasked with the idea of developing a battery, or were you actually working on something else? Because I find that some of my best work is when I'm trying to do one thing and I actually end up finding something else that's more interesting. But I'm just wondering, in this case, were you actually working on batteries? Because I know you were working on some other things with intercalation chemistry at the time. Yes.
So the answer is we were hired to work on any energy-related materials other than oil or chemicals. Mm-hmm. So my initial work was looking at modifying intercalation compounds for their superconductivity behavior.
Mm-hmm. Right.
And the best superconductor was, in fact, a potassium tantalum disulfide. And I could make that in a beaker with KOH and tantalum disulfide crystals, which told me it was really potassium plus TaS2 minus with a lot of energy. So we grabbed on that energy part of it and switched to TiS2 because it's lighter in weight. So yes, you have to grab opportunities, and if something comes up, run with it.
That's right. Okay, I have one more question if nobody else is going to ask anything from here. You just briefly touched on intercalation of sodium and magnesium and showed that there were some issues with that. So what do you think the prospects are for other metals like sodium or magnesium for batteries?
I don't think magnesium has any chance. It's too small, so it diffuses very slowly. Calcium would be better. Calcium also has roughly the same potential as lithium. So magnesium has a knock of low voltage and poor diffusion. But calcium is going to have incredible challenges of plating. I think sodium, if you get the right cathode, is viable. But people should not sell sodium on the basis that lithium is expensive. Lithium is the lowest cost component of the cell, much lower cost than nickel, cobalt, and all the rest of it. So where sodium will come into play is probably on very large batteries where the amount of lithium may not be available. But right now, all the grid folks are just using the same batteries as used for vehicles. So Jay, I can see those Q&As. So there's one about sulfur-based cathodes with multi-electron processes. So the very first material we looked at, and this was back at Exxon, was vanadium diselenide. That reacts with 2 lithiums, but the voltage is too low for the second one. Most of the sulfur ones, the voltage is going to be too low. And the calculations that Anton van der Ven did on TiS2 with magnesium was that the second electron may be around about 0 volts or less than that. So you need a fairly high voltage material to begin with if you're going to use 2 electrons. And that's why we chose vanadium. And I think there's a question from Mr. Park here about 10 to 20 years. What's the future energy storage? I don't know. If I went back 10, 20 years, I wouldn't guess where we are today. But some of the same materials are still going to be used 10, 20 years from now. We're going to be getting into recycling in a big way because most cars last 10 to 15 years. So they'll all be coming into the recycling process. So I expect it's going to be much of the same technology. It'll be better, it'll be safer. I expect it'll be solid electrolytes by then. But no, lithium is the highest voltage, stores the most energy in the cubic volume. So for EVs, I don't think there's too much choice unless we combine it with, say, an efficient fuel cell or with hydrogen. But we're always going to need a battery to give you acceleration. Fuel cells operate at constant output and for regenerative braking.
So here's a question. So how soon can I drive from Rolla to Berkeley, California without having to stop every 3 hours to recharge? You don't have to answer that.
Well, it's a simple answer. Are you willing to pay a few $100,000 for a battery that will take you that far and have to carry itself? How far does your present car drive? Or how far, particularly when you get to my age, can you drive without have a pit stop?
That's right.
So I think most people would say 3 or 4 hours, you're going to want to stop anyway. If you can charge another 150 to 200 miles in 20 minutes. And the recharging stations would like you to go in and buy a donut or a coffee or something as well. So it's all cost.
There's a lot more questions here, but I think maybe we should cut things off here pretty soon. But first of all, I don't know if we can see this, the camera. This is a plaque that we'd like to present to Stan for the presentation of this Stoffer Lecture. And we'll mail this to you. Normally I would shake hands and give you a cheesy smile when I did it, but and then we also have this book, Forged in Gold, that's history of Missouri S&T's first 150 years. So again, we'll mail this to you. And I'd really like to thank Stan again for an outstanding talk and for spending this time telling us about lithium batteries. So let's give him a round of applause.
Thank you very much. Thank you, everybody. And I hope to visit one day when, shall we say, the environment has cleaned up a bit.
Yeah. Thanks. Bye-bye. All right. Thank you.